All right, here in section 6.4, we're going to talk about radians, arc length, and angular speed. First, our objectives are to find points in the unit circle determined by real numbers. We're going to convert between radian measure and degree measure. We've always used degree measure previously to this, so we're going to get into those radians, which are going to be super important, especially advancing into calculus. And then we're going to find coterminal, complementary, and supplementary angles. We've already done all of those in terms of degrees, so again, we're going to be focusing on them in this section in terms of radian measure. So that's our big new focus right here, is doing all those things in terms of radians. Then we're going to find the length of an arc of a circle and find the measure of the central angle of the circle. We'll also convert between linear speed and angular speed and figure out what those two things mean. First, quick review of circles. What do we know about the geometry of circles? Good question. Okay, so circles are, so I'm just drawing one on the XY axis here. Circles are defined by a radius. So if I draw them without a grid, I would define a circle as having a radius. We need the radius in order to find area, for example. So the area of a circle is pi times the radius squared. And I also can use that circle in conjunction with the Pythagorean theorem if I do have it on an XY axis. X, y being a coordinate on the edge of the circle gives me this triangle. So convenient. We've been using that kind of triangle when I've done angles as well. And then the equation for r becomes, by the Pythagorean theorem, x squared plus y squared equals r squared. That's just a squared plus b squared equals c squared. That's where the equation for a circle comes from. Okay, so that's a few things that we know about the geometry of circles. We know their area, and we know their equation if they're written in a standard position right here at the origin. Now, we can generalize that. If the circle is not centered at the origin, this one is. It's got a center at the origin, so I didn't have to do x minus some center value. If it's centered instead at h, k, I can still write its circle as x minus h squared plus y minus k squared equals r squared. Very similar, just having a center in a different location. So this circle would be in a different location, and I believe we've talked about these before as well when we were doing completing the square. So we were writing the equations of circles in that way as well. So that should be a review. When we talked about completing the square, we talked about this form here, I know, as well. Okay. Now, bringing in angles with these. Topic 1, the unit circle. So first of all, a unit circle, what unit means is that it has 1 specifically for its radius. It's not going to have a general radius r, it has 1 for its radius. So the unit circle is the circle with radius 1, and that makes its equation x squared plus y squared equals 1, because r is 1. All right? Now, usually, when I talk about circles, usually when I talk about angles, I talk about angles measured on the unit circle, because it doesn't matter how long the radius is, all the ratios are equal, so we make the radius 1 for simplicity. Okay? So imagine you have a point on the unit circle. Again, unit circle has radius 1, and if we move it around, how far is 1 full cycle? Okay, so if I move it around 1 full cycle, how far is that? The distance that your point is traveling around the circle, if I go 1 full circle, would be its circumference. So I mentioned the formula for area of a circle up here. The formula for circumference of a circle is 2 times pi times r. That would be the circumference all the way around the circle. And so the circumference of the unit circle is 2 times pi times 1. So if I go 1 full cycle, we'll have traveled a distance of 2 pi all the way around, traveling around the edge of the circle. Okay? If I go 2 full cycles, I go 2 pi and then 2 pi again, I'll have gone a distance of 4 pi around the circle. Half a cycle, well, if I'm only going half a cycle, I'm not going all the way around to 2 pi. I should take 2 pi divided by 2, and I'll have pi. So half a circle is going to have a distance of pi. How far will a point go if it travels around the unit circle a quarter of the way? Again, for each of these, we're taking 2 pi as the full way and now dividing by 4. So a quarter of the way would be pi over 4. 3/16 of the way, okay, so that would be 3/16 of 2 pi, and so that would be, if I simplify, the 2 and 16 reduce, gives me a 1 and an 8, so that would be 3 pi eighths. And similarly, I can calculate the distance for any fraction of the circle. So if I go 3/4 of the circle, I meant to say that's 4/3, so it's a little bit more than one full circle. 4/3 of the circle times 2 pi would give us 8 pi thirds. Doesn't matter what the fraction is, I can compute the distance that the point would have to travel to go all the way around the circle. Okay, bringing into the next page here. In general, a point that is traveling around a circle covers how much distance per revolution. Okay, so one full revolution is going to be equal to a distance of 2 pi. Or another way to phrase that is going to be equal to a angular rotation of 360. So now we have a couple different ways to say this. If I go all the way around a circle, I have gone 2 pi in distance, or 360 degrees in terms of a degree measurement. Okay, as usual, we want to be as thorough and precise as possible, so we'll measure the distances around the unit circle starting from the initial point of 1, 0. That's the starting point for our initial edge on the x-axis. And then we're going to travel in a direction that gives us positive angles. So I'm going to label the distances traveled on the unit circle by each point in these cases. Okay, so in this one, I know that 2 pi would be going all the way around, and pi would be going halfway around. So if I count the tick marks, if I count these 1, 2, 3, 4, 5, 6. So each of these has to be a sixth of pi. So this has to be 1/6 of pi, 2, 6, 3, 6, 4, 6, 5, 6. So I get 6 sixths right back here. Okay, so there are 6 of them. If I count 1, 2, 3, 4, 5, 6, getting me back to pi. So then I have 7 6, 8 6, 9 6, 10 6. So this is 10 pi sixths, which reduces to 5 pi thirds. So that would be the distance around to this point. All right, let's take a look at the next one. Okay, so my distance, label the distance is traveling in a circle by each point. The distance would be, I've got all the way around to 2 pi, and then remember, this is pi, that's 0 when you start, so this would be pi halves. So I've gone all the way around to 2 pi. If that's pi, I've gone half of that distance, so another half pi. So I have 2 pi plus pi halves. Since 2 is 4 halves, I can combine that to 5 pi halves in a single fraction. All right? And, this one is going to be interesting because I don't have the fraction for this, but I'm going to assume that since it looks very similar to this picture, that that's also a sixth. So if I count up, I will have gone all the way around. So to get back to here, that's 2 pi, plus to get over to here again, that's another pi, plus, if that's a sixth, just like it was in the first graph, I'll have plus 1/6 of pi. So I have to add up 3 pi plus 1/6 of pi. So 3 times 6 is 18. So 18 plus 1 is 19 sixths. So 19 pi sixths would be the distance.